There is one system inside every refinery, gas plant, manufacturing facility, chemical complex, power island, and process plant that quietly decides whether your operation remains stable or starts falling apart. And most people do not give it the respect it deserves. I am talking about the fuel system, not the glamorous equipment, not the large rotating machines everyone notices, not the advanced control room screens that look impressive during plant visits. Not even the AI dashboards that everyone now wants to put on top of operations. I am talking about the fuel system, the physical, mechanical, process, instrumentation, and control backbone that delivers energy to fired heaters, boilers, turbines, furnaces, process units, and critical utilities. And here is the uncomfortable truth. If your fuel system is weak, your entire plant is weak. You can have world-class process design. You can have an expensive distributed control system. You can have advanced process control. You can have predictive analytics. You can have AI models. You can have intelligent dashboards. But if the fuel does not arrive at the right pressure, right temperature, right viscosity, right composition, right heating value, right dryness, right cleanliness, and right response time, your operation is still vulnerable. Because combustion does not care about design intention. Combustion cares about physical reality. If fuel gas pressure swings too hard, burners become unstable. If fuel gas composition changes too fast, air-fuel ratio control can lose accuracy. If liquid carries over into fuel gas, you are inviting flame instability, equipment damage, and safety risk. If heavy fuel oil is too cold, atomization fails. If asphalt fuel stops circulating, lines can block and the system can become almost impossible to recover without serious intervention. If gas turbine fuel shifts outside WABI index limits, you are no longer managing a utility system. You are challenging the life and stability of the combustor. That's why fuel systems are not secondary infrastructure. Fuel systems are the energy nervous system of the plant. They decide whether energy flows smoothly, whether combustion remains stable, whether emissions stay controlled, whether flaring is minimized, whether backup fuels work when needed, and whether the plant can survive abnormal conditions. And this is where design engineers, automation engineers, AI engineers, process control engineers, and manufacturing engineers need to sharpen their thinking. A fuel system is not just pumps, pipes, vessels, heaters, filters, strainers, vaporizers, tanks, and control valves. A fuel system is a live operating system. It balances production and consumption. It conditions unstable fuel streams. It protects burners. It supports turbines. It reduces flaring. It maintains steam and power reliability. It enables safe startup and shutdown. It provides resilience during emergencies. And increasingly, it is becoming one of the strongest use cases for AI-driven industrial intelligence. But before we talk about AI, let us get the engineering foundation right. The first principle is availability. A fuel system feeding critical consumers must be designed for continuous operation. That means the design must answer a very practical question. What must keep running when the plant is under stress? Which boilers are essential? Which gas turbines must stay online? Which heaters must remain available? Which utility systems must survive during a major trip? Which consumers must operate during startup, shutdown, and boxed-in conditions? Once you answer that, the real design begins. You decide pump sparing. You decide independent drives. You decide whether one pump should be electric and another should be steam turbine driven. You decide whether electrical supplies should come from separate bus bars. You decide how much fuel storage is required. You decide whether the backup fuel system must remain continuously circulating. You decide which equipment can be isolated for maintenance without taking down the full system. You decide whether filters, heaters, vessels, vaporizers, and pumps have enough redundancy. Availability is not a slogan, it is a design architecture. And here is where many systems expose weakness. They may be designed for normal operation, but not for maintenance, not for upset, not for emergency, and not for realistic human operation. If a filter needs cleaning and the plant must reduce load because there's no proper parallel filtration, that is a design weakness. If a heater requires maintenance and there is no adequate standby capacity, that is a design weakness. If a backup pump exists but depends on the same failed power source, that is a design weakness. If a vaporizer is installed but not genuinely ready for fast response, that is a design weakness. If an asphalt system has no effective flushing path, that is not just a weakness. That is a future crisis waiting quietly inside the pipework. The second principle is fuel balancing. In many industrial plants, especially refineries and petrochemical complexes, fuel is not only purchased and consumed, fuel is also produced inside the plant. Process gas, refinery fuel gas, off-spec LPG, low-value liquid residues, flare recovery gas, syngas, low-pressure gas, heavy residue streams. These are not always clean, standardized, predictable fuels. They are variable energy streams, and the plant must decide how to consume them, store them, recover them, blend them, vaporize them, or route them. The goal is not just to burn fuel. The goal is to balance fuel production and fuel demand while minimizing flaring, reducing imported fuel, maintaining stable combustion, and staying within emissions limits. That is why dual-fuel fired heaters and boilers are strategically important. When fuel gas production rises, the plant can increase gas firing. When fuel gas production drops, it can shift toward fuel oil. When gas header pressure falls, makeup gas or vaporized LPG may enter. When gas header pressure rises, large consumers may absorb more gas to avoid flaring. This is not a static utility function. This is a dynamic balancing problem. And if the only thing you are watching is header pressure, you are already behind the event. Because header pressure is often the symptom, not the full story. The real story includes gas composition, heating value, Wabi index, consumer demand, oil-gas firing split, LPG vaporizer response, flare recovery compressor behavior, fuel oil inventory, emissions limits, startup sequence, and equipment availability. This is why AI has a serious role to play, not as decoration, but as supervisory intelligence. A well-designed AI-assisted fuel management layer can anticipate imbalance before the header pressure becomes unstable. It can recommend gas oil split changes. It can predict flare risk. It can warn that a vaporizer may not meet the next demand step. It can identify whether recovered flare gas is beginning to dilute fuel quality. It can help operators act earlier and with more confidence. But AI can only enhance a system that is physically and instrumentally designed well. Bad engineering plus AI is still bad engineering. The third principle is fuel quality. A fuel system does not succeed just because fuel reaches the consumer. It succeeds only when fuel reaches the consumer in a condition suitable for controlled combustion. For fuel gas, that means correct pressure, stable composition, adequate heating value, acceptable density, proper Wabi index, no liquid carryover, no solids, no reactive contaminants, and enough superheat above dew point. For liquid fuel, that means correct pressure, correct temperature, correct viscosity, good filtration, stable blend, no flashing, no excessive coking tendency, and reliable atomization. For gas turbines, the window becomes even tighter. Gas turbines need dry, clean, high-pressure fuel. They are sensitive to Wabi index variation, fuel composition, hydrogen content, contaminants, moisture, and rate of fuel change. A gas that may be acceptable for a furnace may not be acceptable for a gas turbine. That distinction matters. A refinery furnace may tolerate certain fuel gas variations if combustion control is designed properly. A dry, low-NOx gas turbine combustor may not tolerate the same variation without instability, emissions issues, or life reduction. So the correct design approach is always this: start from the consumer and design backward. Do not begin with the header and assume the consumer will accept what arrives. Ask what the burner needs. Ask what the turbine needs. Ask what the boiler needs. Ask what the furnace needs. Ask what the combustion control system can realistically handle. Then design the collection, conditioning, buffering, heating, filtering, vaporizing, mixing, and distribution systems to meet those requirements under all credible operating cases. Now let us look at fuel gas. Fuel gas systems are exposed to pressure swings, composition shifts, condensation risk, LPG enrichment, natural gas letdown cooling, recovered flare gas variability, low pressure source limitations, and possible liquid or solids contamination. A central mixing and knockout vessel is not just a vessel, it is a stability device. It protects against liquid carryover, it provides mixing volume, it slows composition change, it gives the control system time to respond, it helps the plant absorb disturbances. But the vessel must be designed based on real scenarios. What happens when the largest gas producer trips? What happens when the largest consumer trips? What happens when liquid fuel supply to a dual-fired unit fails and gas demand suddenly rises? What happens when LPG vaporization begins? What happens when recovered flare gas contains more inerts than expected? If the design has not tested these cases, the plant has not really validated the fuel gas system. Liquid carryover is one of the most serious fuel gas failure modes. It can happen because of expansion cooling, butane condensation, water saturation, poor heat tracing, poor insulation, natural gas letdown, LPG vaporization, compressor aftercooling, or inadequate dew point margin. The correction is not simply to install a knockout drum and hope. The correct philosophy is to prevent liquid formation wherever possible, then provide separation as protection. That means proper dew point calculation, gas heating, heat tracing, insulation, low point management, knockout vessels, and real-time monitoring. This is one of the clearest AI use cases. Imagine an AI-assisted dew point predictor continuously calculating condensation margin across the fuel gas network. It looks at pressure, temperature, composition, LPG fraction, butane content, ambient conditions, and heat tracing health. Then it warns the operator before condensation risk becomes liquid carryover. That is not hype. That is practical reliability. Now consider fuel gas composition. Many older systems rely heavily on density correction for air-fuel ratio control. That can work when fuel gas is mostly hydrocarbons and hydrogen within a known range. But once inerts, carbon monoxide, nitrogen-rich gas, syngas, or flare recovery gas enter the picture, density may no longer track heating value reliably. Then, the combustion control can become blind. The plant may think it is controlling air-fuel ratio correctly, while the actual heat release and oxygen demand have shifted. That leads to excess oxygen, high CO, high NOx, unstable flames, poor furnace performance, and unsafe margins. The correction is fuel quality visibility. Use analyzers where needed. Use calorific value measurement. Use Wabi index monitoring. Use gas density measurement intelligently. Use predictive soft sensors. Integrate this information into combustion control and operator displays. AI can help by estimating fuel quality in real time even when full composition measurement is slow or unavailable. It can build a fuel quality digital twin that estimates heating value, Wabi index, stoichiometric air demand, dew point, and combustion impact. Now let us talk about LPG vaporization. LPG vaporization can be a powerful backup and balancing tool, but it can also create risk if poorly designed. The vaporizer must have enough capacity. It must have fast response. It must avoid film boiling. It must have reliable heating medium control. It must drain condensate properly if steam heating is used. It must protect against tube rupture and contamination of utility systems. And most importantly, the vaporized LPG must not condense downstream. Butane-rich LPG can create hydrocarbon condensation in the fuel gas header if temperature margin is inadequate. So the design must calculate worst-case dew point and maintain fuel gas temperature above that margin. The AI opportunity is vaporizer readiness monitoring. Do not wait until the largest producer trips to discover the vaporizer is not truly ready. Monitor heating medium condition, coil drainage, liquid level, pressure, temperature, valve position, standby losses, and response history. Give operations a readiness score. A backup system that is not ready is only a drawing. Now consider natural gas backup. Natural gas is usually cleaner and more stable, but high-pressure letdown can create strong cooling. That can cause hydrate formation, letdown valve fouling, and cold gas mixing effects that trigger condensation in other fuel gas streams. The corrective action is preheating, hydrate analysis, downstream temperature control, and careful switchover design. AI can predict letdown cooling and recommend preheat requirements under current conditions before the switchover begins. Now shift to liquid fuels. Liquid fuel design is dominated by viscosity. If fuel oil is too viscous at the burner, atomization fails. Poor atomization means larger droplets, incomplete combustion, smoke, particulates, fouling, flame instability, and poor emissions performance. So fuel oil must be heated enough to atomize properly. But heavy fuel cannot be heated without limit. Overheating can trigger cracking, coking, vapor generation, filter blockage, heater fouling, and tube damage. That is the design tension. Hot enough to pump and atomize. Not so hot that it cracks or cokes. This is especially critical for long residue, short residue, and asphalt systems. Heavy residue systems require storage heating, circulation pumps, fuel heaters, filtration, heat tracing, insulation, flushing, steam out connections, thermal relief, and reliable instrumentation. Asphalt systems are even more severe. The core rule is simple: keep it hot, keep it moving, keep it filtered, keep it controlled, and always be able to flush it. If asphalt circulation is lost, temperature falls. If temperature falls, viscosity rises. If viscosity rises, pumpability drops. If pumpability drops, lines can block. Once lines block, recovery can become difficult, dangerous, and time-consuming. This is why dead legs are dangerous. This is why branch lines must be short. This is why subloops matter. This is why heat tracing must be robust. This is why standby pumps must be kept hot. This is why flushing connections must be strategically located. This is why return control valves may need mechanical minimum stops to preserve minimum circulation. This is why instrumentation redundancy is not luxury. It is survival. AI can transform heavy fuel systems by predicting viscosity at remote consumers, identifying low temperature zones, detecting heat tracing weakness, forecasting filter plugging, estimating heater fouling, and mapping blockage risk. Again, not to replace engineering, to make engineering visible in real time. Filters are another underestimated area. A filter is not an accessory, it is a diagnostic window. If filter differential pressure rises, do not only ask, when do we clean the filter? Ask, why is it rising? Is the blend incompatible? Is asphalt cracking? Is the heater coking? Is storage sludge being pulled into the system? Is the fuel temperature too low? Did the process source change? Did a diluent create instability? AI can classify these patterns. It can connect filter behavior with fuel source, temperature history, blend ratio, heater duty, and previous plugging events. That turns a filter from a maintenance item into an early warning sensor. Now let us address a major weakness in current fuel system design. Many systems are mechanically adequate but digitally weak. They have pumps, filters, heaters, tanks, vaporizers, valves, and trips, but they lack high-quality visibility into developing risk. They are reactive. They alarm after the condition has already become serious. Low fuel gas pressure, high filter differential pressure, low fuel oil temperature, high heater outlet temperature, low surge drum level. These are important alarms, but many are late signals. The future is leading indicators: dew point margin falling, fuel quality shift accelerating, vaporizer response capacity degrading, filter plugging rate increasing, remote consumer viscosity rising, heat tracing circuit underperforming, backup fuel readiness declining, gas turbine Wabi index transient exceeding safe rate. That is where automation and AI become valuable. Not because they look modern, because they reduce surprise. And in industrial operations, surprise is expensive. Surprise creates trips, surprise creates flaring, surprise creates emergency maintenance, surprise creates unsafe work, surprise creates production loss, surprise creates environmental exposure. So if you are a design engineer, your responsibility is to build the physical system correctly. If you are an automation engineer, your responsibility is to make the system observable and controllable. If you are an AI engineer, your responsibility is to convert operating data into prediction, diagnosis, advisory intelligence, and early warning without violating safety hierarchy. And if you are an engineering leader, your responsibility is to stop treating fuel systems as background utilities. Fuel systems deserve serious design review. They deserve dynamic simulation. They deserve failure mode analysis. They deserve instrumentation depth. They deserve AI-ready architecture. They deserve maintenance access. They deserve operator-centered displays. They deserve proper startup, shutdown, flushing and emergency procedures. Because the real question is not, does the fuel system work during normal operation? That is the easiest condition. The real question is, does it work when the largest producer trips? Does it work when a major consumer trips? Does it work when LPG vaporization is suddenly required? Does it work when natural gas backup is introduced? Does it work when the gas turbine must switch fuels? Does it work when a fuel heater fouls? Does it work when a filter plugs? Does it work when heat tracing fails? Does it work when the plant is boxed in? Does it work when the operator has 3 minutes to make the right decision? That is the engineering standard. Days. That is the mindset. Fuel systems are not just energy supply systems. They are reliability systems. They are emission systems. They are safety systems. They are automation systems. They are resilience systems. And now they are becoming intelligent systems. The plants that win in the next decade will not be the ones that simply install more sensors or more AI dashboards. They will be the ones that integrate robust mechanical design, disciplined process engineering, high quality instrumentation, strong control philosophy, dynamic scenario validation, and AI based predictive intelligence into one coherent operating architecture. That is the future of fuel systems design. Not bigger equipment alone, not smarter software alone, but better engineering intelligence across the full life of the system. So the next time someone calls the fuel system a utility package, challenge that thinking. Ask what happens when fuel quality shifts. Ask what happens when viscosity rises. Ask what happens when a vaporizer fails to respond. Ask what happens when liquid forms in the fuel gas. Ask what happens when the asphalt loop cools. Ask what happens when the backup fuel system is needed right now, because that is where the truth of the design is revealed. If this kind of engineering design thinking matters to you, like, share, and subscribe to the channel. For more instrumentation, process control, automation engineering white papers, tutorials, AI and industry insights, and practical design breakdowns, follow and subscribe to www.youtube.com/leadershipnotes. And if you work in design engineering, automation, manufacturing, process control, reliability, or AI for industrial systems, stay close to this conversation, because the future of industrial reliability will not be built by tools alone. It will be built by engineers who understand systems deeply enough to know where failure begins before everyone else sees it.